One might worry about relating rotational or angular displacements to linear displacements. For instance, if someone is going around in a racetrack, we speak of the distance traveled by that person along that racetrack. Usually we don't talk of radians or rotations when we talk about that, but we still can do that. Now, however, how can we relate both? Think also of a wheel that's rotating while moving linearly along the road. Now, how can we relate the rotational displacement of the wheel to the linear displacement of the wheel? Now, one thing that you might remember, if the wheel is going to make one rotation, the distance that it is going to move during that one rotation, if we don't have any slip in, is going to be equal to the circumference of the wheel. What's the circumference of the wheel? It's 2 pi times the radius of the wheel. This is going to be equal to one rotation. Here we have the displacement expressed in units of rotation, units of rotational displacement. Here we have a circumference that's expressed in meters. So we have a relationship between both. Now we can expand this a little bit and speak of this in general. One rotation corresponds to what? The radius times 2 pi. So 2 pi actually corresponds to the angle the wheel has rotated when that angle is expressed in radians. In other words, 2 pi radians is equal to one rotation, or 2 pi radians is equal to 360 degrees. Now, if the wheel rotated a different angle, let's say 30 degrees, then we can find the distance that it had traveled by just multiplying that angle by the radius. And this would be the distance that it traveled. Or that's the distance a person would have moved along the arc of this circle if they rotated by just an angle theta. This would be S and that's theta. So this is one relationship between an angular displacement and a linear quantity. Okay, the same relationship translates into other quantities. For example, the angular velocity omega is actually equal to the tangential velocity. Now, if a person is running with a velocity like this, that would be the tangential velocity over the radius. That's when omega is given in radians per second. Of course, we can rewrite the equation this way. Similarly, we define the acceleration. Alpha, the angular acceleration, is the tangential acceleration over the radius. Okay? Again, if my object is going like this, tangential acceleration is an acceleration that's going to be like this. Let me use another color. That's going to be either like this or like this. That's a tangential acceleration over r. So a change in angular velocity or in rotational velocity has to correspond to the object speeding up along the circle or slowing down. So that's why it has to be the tangential acceleration. It has nothing to do with the centripetal acceleration. It's not related to that. That's very important. Alpha is not related to the centripetal acceleration. It is related to the tangential acceleration.